Hello everyone. In the previous class we have discussed about the trapezoidal rule, Simpson rule and their error. Trapezoidal rule is what? Trapezoidal rule is integration from the a to b of the function fx is equivalent to b minus a upon 2 f of a plus f of b, or we can replace this b minus a by h equal to b minus a. Simpson was, and the error in trapezoidal rule is minus h cube upon 12 f double dash c. Simpson 1/3 rule. Simpson 1/3 rule is integration from a to b fx dx equal to h upon 3 f of a plus 4 f of a plus b upon 2 plus f of b, where h is b minus a upon 2. Okay, error in this case minus h5 upon 90 f4 c, where c is what? That is the maximum value, that is the value inside the interval AB. Okay, so let's do some example based on it. Compare the trapezoidal rule and Simpson rule to approximate zero to 2 fx dx when fx is x4 and fx equal to 1 upon 1 plus x. Also find the absolute error and maximum bound for the error. Okay. Solution. So what you have to do, you have to find out integration of the function by the trapezoidal rule and Simpson rule, and then we have to compute absolute error and maximum error bound for the trapezoidal rule and Simpson 1/3 rule. So let us integrate it. Trapezoidal rule. Okay, so 0 to 2 x4 dx, it is coming out to be h by 2 b minus a upon 2. So 2 minus 0 upon 2, function value is x4, so f of 0 plus f of 2, that is what 1. F of 0 is 0, f of 2 is what? 2 raised to power 4. So the value is coming out to be 2 raised to power 4. Okay, now compute the value, that is 16. Now Simpson 1/3 rule, integration by Simpson 1/3 rule, 0 to 2 x4 dx equal to b minus a upon 2. H, what is h here? 2 minus 0 upon 2 upon 3. This is your h. Your h. F of a, f of 0, 4 into f of 0 plus 2 upon 2, that is the midpoint, f of 1 plus f of 2. So the value is coming out to be 1 upon 3, 0, f of 1 is 4 plus 2 raised to power 4. So the value of the integration is coming out to be 20 upon 3. Okay, absolute error. So this is by Simpson rule. Absolute error when using trapezoidal rule. Absolute error, that is I exact minus I trapezoidal rule and I exact minus I Simpson rule. I exact is what? Integration. If we are finding I exact, that means the exact value of the integration. So 0 to 2 x4 dx is coming out to be what? x5 upon 2. x5 upon 5. Value of the integration 0 to 2, that is 2 raised to power 5 upon 5. Okay. That is 32 upon 5. So error by the absolute error by the trapezoidal rule is what? 32 upon 5 minus 16. This is the error we are getting. Okay, that is 48 upon 5. 48 upon 5. Error, absolute error by the Simpson rule, it is coming out to be 32 upon 5 minus 20 upon 3. So the error is coming out to be 4 upon 15. So these are the error by the trapezoidal rule and Simpson 1/3 rule. So if you compare, then this error is less in comparison to the trapezoidal rule. Why we will discuss later on. Now the error bound. Error bound by error bound in trapezoidal rule. Okay, what is the formula? Minus h cube upon 12 f double dash c. H is what? That is b minus a, that is 2 whole cube upon 12 f double dash c. What is the function here in trapezoidal rule? What is the function here? That is x4, f dash x is what? 4 x cube, f double dash x is what? 12 x square. That is the interval is what? We are having interval 0 to 2. What is the maximum value? Maximum of f double dash x in 0 to 2. So obviously it is x square in the numerator. As x is increasing, the function f double dash is x is also increasing. So c will be what? In this case, c is what? Where the function derivative, second derivative of the function is having maximum value. C is what? That is 2. So f double dash c equal to what? 12 into 2 square. That is 48. Okay. So error bound, in this case trapezoidal rule, it is coming out to be minus 16 upon 12, sorry, 8 upon 12 into 48. We are generally taking error in positive. It is coming out to be 32. Okay. So now, so this is a large error. Now we are taking error bound in by Simpson 1/3 rule. Simpson 1/3 rule. So whenever we are having, what is the formula for the error bound? It is in Simpson rule minus h5 upon 90 f4 c. So fx is x4, what will the value of fourth derivative? F dash x is 4x cube, f double dash x 12x square, f triple dash x 24x, f fourth derivative of x 24. So error bound is what? Minus h5. H is what? b minus a upon 2, that is 2 minus 0 upon 2, that is 1. So minus 15 upon 90 into 24. Okay, so the value is coming out to be 4 upon 15. Okay, so this error bound, if we compare between the Simpson 1/3 rule and trapezoidal rule, then the error bound in the case of trapezoidal rule is 32 and Simpson 1/3 4 upon 15, that is less. So the error will be less than 4 by 15 in Simpson 1/3, 4 by 15 in Simpson 1/3 rule. So Simpson 1/3 rule have better accuracy than trapezoidal rule. Why? It will discuss in the after this example. Okay, this is the first part, it is over. Now next part, when the function is 1 upon 1 plus x. So what is the value of the integration? Exact value of the integration, it is 1 upon 1 plus x dx 0 to 2, it is log of ln 1 plus x, integration value 0 to 2, it is coming out to be ln 3, that is 1.0986. Okay, now a is what? 0, b is what? 2, and h equal to b minus a, that is 2. Then trapezoidal rule, it is 2 upon 2 f of 0, so 1 upon 1 plus 0 plus 1 upon 1 plus 2. The value is coming out to be, this integration value is coming out to be 1 plus 1 upon 3, that is 4 upon 3. And Simpson 1/3 rule, that is h is what here? 2 minus 0 upon 2, that is 1. 1 upon 3, 1 upon 1 plus 0 plus 4, 1 upon 1 plus 1 plus 1 upon 1 plus 2. This integration value is coming out to be 10 upon 9. So here error, absolute error is coming out to be 1.0986 minus 4 upon 3, and the value of the error is coming out to be 0.2347. 0.2347. So this is the absolute error. Okay, in this case absolute error will be what? 1.0986 minus 10 upon 9. So it is coming out to be 0.0125. Okay, so this error is less. Now error bound trapezoidal rule, it is minus h cube upon 12, 2 upon cube upon 12, f double dash c. Okay, the second derivative f double dash c. So f of x is what here? 1 upon 1 plus x, f dash x will be what? Minus 1 upon 1 plus x whole square, f double dash x 2 upon 1 plus x whole cube. So maximum value of f double dash x in 0 to 2 will be what? It will be at 0, because 1 upon x, 1 plus x is in the denominator and when x is increasing, then 1 upon 1 plus x is decreasing. That's why it is a decreasing function. We want maximum value of f double dash x. So it will be what? It will be, so the maximum value of double dash x will be at 0. So that's why the maximum value of f dash, it is 2. So c will be what here? That will be 0. So error bound will be what? It will be minus 2 cube upon 12 minus 2 cube upon 12 into, that is 2. Okay. Error bound in Simpson rule. Error bound, it is coming out to be minus 2 raised to a 5 upon 90 into 4 derivative of the function. F4, see, you can compute 4 derivative by yourself. I am writing the directly value of the, that is 4 upon 15. I have done some mistake, it is 10. Okay, so this is 4 upon 15. So this is the error found in Simpson rule. So here we have discussed example based on trapezoidal rule, Simpson 1/3 rule, and here we found out that the error in trapezoidal rule is more in comparison to the Simpson rule. That means Simpson rule is more accurate. Why it is so? Let us discuss in term of accuracy. So that we are discussing about the degree of precision. Degree of precision of Newton-Cotes formula. So the degree of accuracy or precision of a quadrature formula is the largest positive integer n such that the formula is exact. The formula is exact for x raised to power k for each k equal to 0, 1, 2 up to n. So degree of accuracy or precision of a quadrature formula. Here we are having we have discussed about the Newton-Cotes formula, and quadrature formula we call as trapezoidal rule and Simpson 1/3 rule. So degree of precision of these quadrature formula is the largest positive integer n such that the formula is exact for x raised to power k. That means if the formula is exact, that means this formula gives the exact value of the integration. That means the error is 0 up to a polynomial of degree k. Then we'll say the degree of precision is what? That is greater than k. That means k plus 1 is the degree of precision of that formula. Okay. So degree of precision of the formula will be what? That is the maximum value of that k. Till for that the formula is exact. So we can write here, first point is what? The degree of precision of a quadrature formula is n and only if the error is 0 for all polynomial of degree k equal to 0 to n, but it is not 0 for some polynomial degree n plus 1. Okay, if k equal to n, then degree of precision of the quadrature formula k equal to n is the degree of precision of the quadrature formula if the error is 0 for all polynomial of degree k equal to 0, 1, 2 up to n, and error is not 0 for some polynomial of degree n plus 1. Okay. Second point. So trapezoidal rule has degree of precision 1, because the error formula of trapezoidal rule is what? h cube upon 12 f double dash. See, if we are taking fx is a polynomial of degree, fx is constant or x. Okay, so error will be what? Error is 0, because the first derivative of constant is 0, second derivative or the second derivative of x is 0. If we are taking fx equal to x square, in that case error is not equal to 0. So that's why the minimum degree polynomial for which error is not 0, that is what n equal to 1. So that's why degree of precision for the trapezoidal rule is what? 1. And Simpson 1/3 rule, degree of precision is what? That is 3. Why? Because the error formula contain h5 upon 90 f4 c. If we are taking fx equal to maximum x cube, then fourth derivative f4c will be what? f4x if we are taking, that is what? 0. If we are taking f of x equal to 4 degree polynomial, then error is not equal to 0. That's why degree of precision for the Simpson rule is what? 3. Okay. So that's why degree of precision of Simpson rule is more than the trapezoidal rule. That's why Simpson rule gives better accuracy than the trapezoidal rule. That is the reason. So third point is what? It is observed that higher degree of precision gives better accuracy So Simpson 1/3 rule yield more accurate estimate than the trapezoidal. Okay. Now there is one example. The quadrature formula formula 0 to 2 fx dx equal to c0 f of 0 c1 f of 1 plus c2 f2. This is some other quadrature formula different from trapezoidal Simpson 1/3 rule. So any integration we are writing in terms of discrete form, then it is called quadrature formula. Is exact for all polynomials of degree less than or equal to 2, then determine C0, C1 and C2. So it is given here in this question. This quadrature formula is exact for all polynomials of degree less than or equal to 2. So the degree of precision given here 2. It's given that formula is exact for all polynomials degree less than or equal to 2. Therefore we have fx equal to what? 1 x square. So fx can take value, constant value, 1 degree polynomial and 2nd degree polynomial, and then compute the integration value. So we'll put fx on the left hand side 1 dx 0 to 2, on the right hand side c0 f0 is what? 1 plus c1 f of 1 is 1, c2 because it is constant for all values of x. So it is coming out to be c0 plus c1 plus c2 equal to integration of 1 is what? X. This is 2. c0 plus c1 plus c2. Okay, so what we have to do? We have to compute the value of c0, c1, c2 with this condition. Now fx equal to x. So 0 to 2 x dx x square by 2, that is 2 square upon 2 equal to c0 constant plus c1 f of x, c0 f of 0, c f of 1 f of 2. c0 f of 0 is 0 plus c1 f of 1, that is what? 1, c2 f of 2, the value is coming out to be c1 plus 2c2. This is the equation 2 equal to c1 plus 2c2. This is the next equation number 2. Now fx equal to x square 0 to 2 x square dx x cube upon 3, that is 8 upon 3 equal to c0 to 0 plus c1 2 square c1 fx equal to x square, so the value will be what? 1 square plus c2 f of 2 is what? 2 square. So this is the value coming out to be 8 by 3 equal to c1 plus 4c2. Now solve equation number 1, 2, 3 together. We are getting the value as c0 is what? This is 1 by 3, c1 is 4 by 3 and c2 is 1 by 3. So the quadrature formula 0 to 2 fx dx is coming out to be what? It is 1 by 3 f of 0 plus 4 f of 1 plus f. By chance it is coming out to be Simpson 1/3 rule, nothing else. But it is not necessary that always you are getting the known formulas. Okay, similarly one more example we are having here 0 to 1 fx dx equal to c0 f of 0 c1 f of x1. Find the constants and so that the quadrature formula so the given quadrature formula has highest possible degree of precision. Okay, solution. So fx equal to 1, then we are having integration 1 dx equal to 1 c0 plus c1. fx will choose as x. So how many things we have to compute? That was c0, c1 and x1. So maximum, in order to compute these 3 unknowns, how many conditions we are required? We require 3 conditions. So we are starting from fx equal to 1, then fx equal to x, then fx equal to x square. So it is coming out to be 1 by 2 c1 x1. fx equal to x square, then integration is what? X square dx 0 to 1, it is coming out to be 1 by 3 c1 x1 square. Compute the value of these constants, like there are 3 conditions, so that you can compute the value of c1, c0 and x1 from these 3 equations. The value of c0 is coming out to be 1 by 4, c1 is 3 by 4 and x1 is 2 by 3. Okay, so these are the value we have obtained. We can write the formula as 0 to 1 fx dx equal to 1 by 4 f of 0 plus 3 by 4 f of 2 by 3. It's the formula. So next is composite numerical integration. Composite numerical integration. What is composite numerical integration? As the name express that composite. So we have to compose numerical integration. That means till now what we have done, we have derived trapezoidal rule and Simpson 1/3 rule. We have taken the interval a to b as in trapezoidal rule a to b as one subinterval, and in Simpson 1/3 rule we have divided the interval into 2 parts. Okay, x0 to x1, then x1 to x2. Then we saw that the Simpson 1/3 rule gives better result than trapezoidal rule. So now we are using the technique to divide interval into some interval so that we can get better accuracy. How we can do that? Let us, and why we are required to do that? If we are taking trapezoidal and Simpson 1/3 formula are based on power of h and then the derivative of the function. So if h is large, when h is large, h is what? That is the length of the interval. and Simpson rule, and this is in trapezoidal rule. Okay, when h is large means what? That means b minus a is large. When h is large, then error will be what? Error is what? If we are talking about the trapezoidal rule, h cube upon f double dash c upon factorial, not factorial, it is 12. Okay, so if h is large, then h cube is also large. H is large, then h cube is also large. In that case, error is also large. The same thing is with the Simpson rule. H is large, h5 is large, that's why the error is large. But if error is large, that means it is a numerical solution is very different from the exact solution, exact integration. Okay, so numerical integration is different from the, this implies that numerical integration is away from exact integration. When this is the situation, then whatever integration we did, that is useless. So that's why we are using composite numerical integration. Composite, that means we will try to reduce length of the interval. Okay, we'll try to reduce this h. Okay, so that we are going to do in this section. So let us write in words, or we first will do composite numeric trapezoidal rule. So now we'll discuss composite trapezoidal rule. What is composite trapezoidal rule? We divide the interval a to b into n subintervals with step size h equal to b minus a upon n. So we divide the whole interval ab into n subinterval with a step size b minus a upon n, and taking nodal points a equal to x0, x1, x2 up to xn equal to b, where x1 is what? x0 plus h, xi is equal to x0 plus ih. We can say x2 is x0 plus 2h and so on. Xi can be written as x0 plus ih, where I equal to what? 0. 0 is what? That means x0 we can get 1, 2 up to n. Okay, so let us take integration a to b fx dx as x0 to x1. So just try to understand, interval is what? This is the interval a to b. We divide it into subintervals. First interval was what? That is a to b. Okay, if we are taking simple trapezoidal rule, then the length will be what? B minus a, length of this interval. But we are using composite trapezoidal, so we will compose the interval ab into subintervals. So we will write a as x0, this is x1, x2 and so on, this is xn. So xn is what? That is b, x0 is what? That is your a. So we will write this integral a to b fx dx as integration from x0 to x1 fx dx plus x1 to x2 fx dx, x2 to x3 fx dx plus xn minus 1 to xn fx dx. Okay, so now we have divided the whole interval a whole integration from a to b into integral in each subintervals. Okay. Now a to b fx dx equal to, now apply trapezoidal rule. Now apply trapezoidal rule for each subinterval. Okay. Now applied this trapezoidal rule. Trapezoidal rule for each subinterval. Okay, so what we are getting? We are getting here a to b fx dx equal to x0 to x1 fx dx and so on, plus xn minus 1 to xn fx dx. Now trapezoidal rule. What is happening? So this integration x0 to x1 fx dx plus x1 to x2 fx dx xn minus 1 to xn fx dx. Now apply trapezoidal rule here. It is coming out to be x1 minus x0 upon 2 f of x0 plus f of x1 plus x2 minus x1 upon 2 f of x1 plus f of x2 and so on, plus xn minus 1 upon 2 f of xn minus 1 plus f of xn. It is coming out to be each here xi plus 1 minus xi equal to h, or I equal to 0, 1, 2 up to n minus 1. So we can write it h upon 2 f of x0. x0 is what? That is a, plus f of x1, and f of x1 is repeated. So this is what? This is also h. Also h. Okay. So what we are getting here? We are getting fx1, fx1. It is repeated twice. So 2 f of x1 plus 2 of f of x2. All terms are repeated except endpoints, and so on, plus f of xn. This xn is what? B. So we can write it here h by 2 f of a plus f of b plus 2 into, taking 2 outside, then f of x1 plus f of x2 f of xn minus 1. So this is the composite trapezoidal rule. This is composite trapezoidal rule. Next we will derive composite Simpson 1/3 rule. Composite Simpson 1/3 rule. Composite Simpson 1/3 rule. In composite Simpson 1/3 rule, what we have to do? Before that, one more thing I want to explain here. If we see here, okay, if we want to explain it graphically, so what is happening? This is your function fx, this is the point A, this is the point B. Okay, then we are dividing it, this interval, into sub-intervals. Okay, and so on. So this is the point x0, x1, x2, x3 and so on. This is up to xn. So we are approximating this function with the help of a straight line. Okay, so we are getting some error here. So this is the situation if we compare with the simple trapezoidal rule and composite trapezoidal rule. In composite trapezoidal rule, the error is less in comparison to the previous case. If we are taking previous case, then the whole interval is length is what? That is your h. But here we are having this h is what? H is xi plus 1 minus xi. That is smaller than the previous case. So error will be what? Error will also be reduced. Okay. So trapezoidal, this is the composite trapezoidal rule. So we can say here, suppose this is xi minus 1, this is xi. So the part between, this is the error. So this green line is what? It is approximated by the straight line, and red is what? That is the function. So we are getting less error in comparison to the previous case. Okay, next is Simpson 1/3 rule. If we are talking about Simpson 1/3 rule, Simpson 1/3 rule. This is trapezoidal rule. Okay, Simpson 1/3 rule. What is happening? Suppose the function is, okay, this is your x0 point, this is your xn point. Okay, now we are dividing this interval into small subintervals. Okay, but in Simpson 1/3 rule we are taking 3 points together. Okay, we are approximating it with the help of a polynomial. So this is the polynomial, this is the polynomial we are taking here. Okay, this is x0, x1, x2, x3, x4 and so on. Okay. This is your function fx and this is the p2x. So whenever we are applying Simpson 1/3 rule, then if we are taking 3 points together, x0, x1, x2 and then x2, x3, x4. Okay, so we have to take 3 points together. So n should be what? N should be even. N should be even here. Otherwise one of the point will remain left. So area will not be covered completely. So whenever we are dividing whole interval a to b into subintervals, then the number of n, it should be what? It should be even. N should be even. Okay, if we are saying suppose n equal to 4, n equal to 4 means what? Suppose this is the function. So 1, 2, 3, 4. So this is what? This is x0, x1, x2, x3, x4. So interval will be what? It will be odd. 1, 1, 2, 3, 4. Sorry, interval will be even, but the number of nodes will be odd. But since we are starting from 0, that's why the final point xn, n should be even. Okay, so it should be clear. So next is